We now need to develop a concept of velocity. Obviously, a particle can move from one place to another. One way we can think of this particle moving is this object, as it moves along, is at a given x0, x1, x2, and x3. Every time, let's say, it emits a beam of light, or it flashes, then it's at a new place, and then a new place after that. If we imagine this particle moving along on some path, here's the path right here, we could imagine it at a point x mu right here, where it gives one flash of light, and then an infinitesimal time later, this infinitesimal length here, dx mu, it's at the position x mu plus dx mu. Now the length of that interval we already know is d tau, which is the square root of g mu nu dx nu. We also know from our previous work that c dt divided by d tau is 1 over the square root of 1 minus v squared over c squared. If we go to a frame of reference that moves exactly with the particle, then velocity is equal to 0, and d tau, as we discussed previously, is c times dt. Therefore, we can say that d tau is the time that has elapsed at rest on a particle, or at a clock, using a clock that is at rest on a particle. So if we imagine a clock that sits on this particle as it moves around, d tau measures the infinitesimal time between one flash of light and another flash of light emitted by that clock. In relativity, we must take derivatives with respect to d tau because it's a scalar, and not with respect to dt, which transforms as part of a 4-vector. Therefore, we now want to define the 4-vector velocity, v mu. That means there are 4 components, mu is equal to 0, 1, 2, 3, as by definition a constant c times dx mu times d tau. Each of those changes divided by d tau with respect to the time interval on an invariant clock that sits on that particle. We put this constant c out front because you'll recall that dx and d tau have the same units, which are meters. Therefore, this quantity is dimensionless, and we multiply by c to maintain the dimensionality of our velocity as having meters per second. Therefore, we can write v mu as its 4 components as c dx naught d tau and dx r dr d tau. Using our previous equation for dx naught d tau and multiplying through by c, we find that this is c over the square root of 1 minus v squared over c squared for the first component, and the second component is c times c dt over d tau dr over c dt. Now the c dt and the c dt of course are cancel, and that's just c times dr d tau, which we began with. We have broken this up so that one can see explicitly the velocity dependence and so forth. The term right here is obviously the velocity v, the c's cancel, and we're left with a factor 1 over the square root of 1 minus v squared over c squared, exactly as we are in the first term. That gives us the 0th component of velocity and the regular component of velocity. We notice that the regular component of velocity in relativity, that's vx, vy, and vz, differs from the velocity that Newton would use by this factor 1 minus v squared over c squared, the reciprocal of that square root. And therefore the velocity is almost identical up until we get to about 1/10 of the speed of light. Velocity now has another component, which is c divided by the square root. And that's called the naughth component of velocity, and it will have a very interesting use in just a little while that's related to the energy. We note that the length of the velocity vector g mu nu, v mu, v nu, is equal to c squared, and that is always an invariant. In other words, the length of the velocity 4 vector of every single particle is the square of the speed of light. That's not a contradiction. It turns out that it's true simply by the way the nth component is defined with respect to the vector part of the component. We now want to look at two interesting aspects that arise in relativity: the Lorentz contraction and time dilation. The Lorentz contraction for an interval is defined in the following way. Let's look at the primed frame for the Lorentz transformation versus the unprimed frame using the more normal notation where we use the square root of 1 minus v squared over c squared in the denominator, and this format right here. Let's look at these as equation A and equation B as relating to how an interval dx and dx naught are related between a frame S and a frame S prime that's moving with respect to that. First of all, let's take equation A. We want to choose events that are in the same place in frame A. These are events that occur exactly at the same place, and if these events occur in the same place, then dx, the change in x, is going to be 0 between those two events. For equation A, this means that dx naught prime, which is c dt prime, is going to be equal to c delta t over the square root of 1 minus v squared over c squared. This is the time interval for events that occur in the same place. Thus, d tau is the time interval on the particle that's moving, because in this frame of reference, these two events occur in the same place. We set delta x equal to 0. Therefore, in this frame, between the first part of the infinitesimal and the next part of the infinitesimal aspect between the two events, there's no change in space. Therefore, dx naught sits on the particle. Therefore, it follows that the time interval in any frame, primed frame, is equal to the time that passes in a frame of reference and a clock that sits on the particle divided by the square root of 1 minus v squared over c squared. If we look at this, of course, at low velocities, this is essentially equal to 0 right here, and so the times run at the same rate. But as we near the speed of light, this term becomes near 1. We have 1 minus 1, which is 0. 0 into this explodes, so this term becomes infinitely large. Therefore, the time as seen by an observer who sees the object as moving is much, much longer, and that's why we say that this refers to a time dilation. When you see someone run by you at extremely high speed near the speed of light, the time between their heartbeats might occur in days or months or even years. You see their time as slowed down or dilated according to this equation. Remember again, x naught sits on the particle. That's the watch or the heartbeat of the guy who's jogging, who's running, and you're sitting on the sideline watching that runner go by. Likewise, we can look at equation B, and in equation B we want to now do something different. We want to look at simultaneous events in the frame S. If we look at simultaneous events in frame S using this equation, then of course for simultaneous events delta x naught is equal to 0, and we have delta x prime is equal to delta x over the square root of 1 minus v squared over c squared. Now, that means that if frames are simultaneous over here, then they occur at the same time. If an object were to go by you and you took a photograph of it and photographed it in your frame, then you would be choosing a simultaneous measurement of one end and another end of that object when you did the photography as that object moved by you. Therefore, the frame S is used to simultaneously measure, say photograph, the natural length in S prime. Consequently, L is equal to the natural length is the length in the primed frame, because the other length was used, the other frame was used for the photography, and we can say that the natural length here is equal to the length that you observe divided by the square root, or the length that you observe is the natural length times the square root of 1 minus v squared over c squared. Since this term gets smaller and smaller, it means that the length itself gets smaller and smaller, and this is called the Lorentz contraction. As we get near the speed of light, we find that objects actually have a smaller and smaller dimension or length in the direction of motion until finally, at the speed of light, they shrink down to have zero dimensionality in that direction, or zero length. These two effects, time dilation and Lorentz contraction, are absolutely key to understanding how we see things in another frame of reference. One of the most critical aspects of relativity, and the most difficult to understand, is that every observer is symmetric with respect to every other observer. For example, if you and I run past each other going in opposite directions, I see your heart beating as slow, much slower than mine because of time dilation, and I see you as being thinner in the direction of motion. The hard part to understand is that you will see me in the same way, so that everything is absolutely symmetrical. You see my heart as running slower, and you see me as being thinner in the direction of motion. We understand how coordinates transform under the Lorentz transformation. And because we divided by a scalar, we were able to form an object called the forward velocity, or the velocity vector, and it obviously transforms exactly like the position transforms. In fact, it turns out that we can define, in general, an object called a covariant vector if the components of that object transform exactly in the same way under a Lorentz transformation that the other objects, the coordinates, transform. We can also define a covariant vector. A covariant vector is related to the contravariant vector by multiplying by the metric tensor g mu nu. You recall that g mu nu with two lower indices is equal to a plus 1, minus 1, minus 1, minus 1. Therefore, it follows that for any vector whose components are lowered, a0, a1, a2, and a3, these are lower components here, that those lower components will be equal to the upper or natural contravariant components by the difference in a sign. In general, it's very important to understand that if we take any one of the spatial indices and lower an index 2 down to 2, it will change the sign. Likewise, if we raise it, it will change the sign. But a sign is always unchanged for the zeroth component. This is just a property of the metric. We can define a tensor of rank n as an object which has n indices, mu1, mu2, up to mu n. For example, t, mu1, mu2, up to mu n. If each of these indices transforms independently under L mu nu. Thus, how does this object change when we go from one frame to another? Well, it changes by having each of the indices transform under the Lorentz transformation, which is given exactly by this equation here. If t is the tensor according to one observer, then the tensor according to a moving observer has the following components, where nu1 is changed into mu1 with this summation, nu2 summed over nu2 with mu2. Likewise, up for all of the n different components. Now, if you think about how large this object is, these are 4 components and these are 4. So a tensor of the second right has 16 components and is often referred to as a matrix. because we can think of it as an array. If we think of one with 3 components, it becomes like a cube of numbers. 4 times 4 times 4 numbers. In general, with n, it is 4 to the nth power, different numbers that make up this object. So something with, say, 10 different indices is absolutely huge because it's 4 times 4 times 4 times 4 up to 4 to the 10th power. Different objects. These are all mixing up with one another under the Lorentz transformation in a way that forms that many new objects. Let's look at some very special tensors for the theory of relativity and review those. Obviously, the most important tensor is the tensor g mu nu. And it has the same 2 lower indices as 2 upper indices. The reason for that is the off-diagonal elements always vanish. And so you can only have diagonal elements 1, 1, 2, 2, 3, 3, or 0, 0. Obviously, if I lower 2 of the 0 components, I don't change the sign. And if I lower 2 that are 1s, 2s, or 3s, I must change the sign twice, one for each index, consequently leaving it unchanged. It therefore follows that g mu nu with lower indices and g mu nu with upper indices is the same tensor. Another interesting tensor that one can form is a contraction between a tensor g mu nu and a g nu rho. That gives a tensor when I sum over nu, 0, 1, 2, and 3, which you can figure out very quickly is the function delta mu, and you can see the only free indices are mu and sigma. So we have a delta mu sigma, and that delta mu sigma is exactly the tensor with 1s down the diagonal and 0s off diagonal. It is the Kronecker delta. It turns out in n dimensions that one can form a very interesting other type of tensor, the totally antisymmetric tensor. The totally antisymmetric tensor in n dimensions always has n indices. In other words, in 4 dimensions, you must have 4 indices. In 3 dimensions, you must have 3 indices. In 2 dimensions, 2 indices. And in every dimensionality of space, it's defined the same way. It's defined as being a plus 1 if these indices, mu1, mu2, up to mu(n), is an even number of transpositions or permutation of 1, 2, 3, 4, 5, 6, 7, 8, whatever we have up to n. It is minus 1 if it is obtained from that sequence, 1, 2, 3, 4, 5, 6, 7, 8, 9, n, by an odd number of transpositions, or it's sometimes called an odd permutation. If it can't be obtained by an even or an odd number, then the tensor is 0. In particular, a tensor that has 2 identical components can never be obtained from one where you have a permutation of 1, 2, 3, 4, 5 up to n. Consequently, anytime you have 2 identical indices or more identical indices, this tensor vanishes. Again, this is called the totally antisymmetric tensor. Some examples of this tensor are epsilon 1, 2, 3, and since that is a symmetric ordering of the normal order, this is defined as 1. But if we do one transposition, which is an odd number, and interchange 2 and 1, we get epsilon 2, 1, 3, and that's by definition a minus 1. If we were to now change this to 2, 3, 1, by interchanging these two, we'd have 2 transpositions, which would change it back to a plus 1 again. Likewise, the tensor in 4 dimensions is epsilon 0, 1, 2, 3. We define it to be a plus 1. Therefore, if I interchange the first 2 and the second 2, I get a 1, 0 and a 3, 2, which gives me a plus 1. But if I interchange the 1 and the 2, which gives me 1 transposition, I get a minus 1. Again, this tensor, epsilon mu 1 to mu n, is called the totally antisymmetric tensor. In 3 dimensions, that tensor is used to create what is called the cross product. Now that's a very unusual circumstance. and it only happens with 3 dimensions. In 4 dimensions, there is no cross product of 2 vectors. One gets an entirely different type of structure, namely what is called the dual tensor. So this happens here in 3 dimensions because of the epsilon symbol, which means that we can take the 3 components here, the 3 components here of K, and contract those and be left with one component which transforms as a vector. So C, which is by definition Ci is epsilon ijk summed over j and j bk, is automatically a vector because it has one index. Again, an object with no indices is called a scalar, with one index a vector, 2 indices and more a tensor, but specifically 2 is often called a matrix. We notice also that an upper index is called a contravariant index and a lower a covariant index. The change between any covariant and contravariant indices is always accomplished by using the metric tensor. We can take any index and lower it, and any index and raise it by simply multiplying by this index and contracting, and therefore summing over all 4 indices.